Hello and welcome to this session. So in this session, I'm going to talk about the methods of integration. And in particular, we want to talk about two main methods of integration. Integration by substitution and integration by parts. Of course, there are many other methods of integration, but we're going to talk about the two main methods. So one is the integration by substitution. At the integration by substitution, we're going to discuss the algebraic substitution and also the trigonometric substitution. So the first one is the algebraic substitution. So this method involves to the integrals where the integrand is a product of two functions or is a quotient of two functions. That is, we have a numerator which is a function of x and the denominator which is also a function of x. And the third case is where the function is expressed as a composite function. But in all the three cases, one of the functions should be a derivative of the other. In particular, for the quotient, the method applies when the numerator is a scalar multiple of the derivative of the denominator. So that in general, this method will apply to the integrals that take the form. One is a product, but where one of the functions appearing in that product or one of the functions appearing in the integral is a derivative of the other. So that we have k is a constant here, k times f prime of x multiplying f of x. F of x may be raised to some power n. In the case of the numerator, or rather in the case of the quotient, we have something similar to the product. But in this case, in particular, it is the numerator that should be the derivative of the denominator. Then the third case is the composite function. And in the composite function, the derivative should appear in the integrand. So in all the three cases, one of the important things is that the derivative should appear in the integrand. We have a function f of x and its derivative. Now, for these functions, or for these integrals, the transformation u is equals to f of x will reduce the integral into some standard format, into the standard form. So we are going to look at examples on how to apply this method to different cases. So before we go to the example itself, we have said that the transformation u will reduce the integral to some standard form. What do we mean by the standard form? The standard form is the form where the integrand or the integral can be achieved by the use of the rules of integration. So basically, if you look at the first integral, for example, if you set u to be equals to f of x, then we can find du by dx as f prime of x. And this is the key to this method, that when you differentiate the function, you get f prime, and f prime appears here. So because we are going to be substituting, then we make dx the subject here, which will be du divided by f prime of x. And once we do this, then we substitute. So in this integral where we have k times f prime of x times f of x raised to power n dx, now this becomes the integral of k f prime of x, then u raised to power n, then du divided by f prime of x. And you see now f prime of x appears in both the numerator and the denominator, and this one cancels out, so that the result is that we get k times the integral of u raised to power n with respect to u. And we can easily now achieve the solution here by using the rules of integration. K u raised to power n plus 1 divided by n plus 1 plus some constant. So this is the idea about the algebraic substitution. Algebraic substitution. So when you're given a problem and you want to apply this method, the key is to check, do we have a function f of x and its derivative, or a scalar multiple of its derivative appearing in the integral? If that is the case, then we use this method. Let's do an example. Example here we have the integral of 2x times e raised to power x squared. Now, this can be seen to be a function of another function, or a composite function. That is the exponential function raised to some function f of x. This can be regarded as the function of the function, so that if we take our function here, f of x, to be x squared, then we see that f prime is 2x if we differentiate that. And we notice that 2x appears in this integral. So because we have 2x, e raised to power x squared. Meaning that now we can take our u to be x squared, then we differentiate u with respect to x to get 2x. Then we make dx the subject, so that we have dx is equals to du divided by 2x. And now we are going to substitute back. Our integral is 2x e raised to power x squared. We are replacing x squared with u, and then dx with du over 2x. So we have 2x e raised to power u du over 2x. And clearly you see that now the 2x here cancels with this other one, so that the integral reduces to e raised to power u du. And now this one is in the standard form. We integrate e raised to power u with respect to u to get e raised to power u plus a constant. But we remember that u is equals to x squared. So we substitute back. We substitute back x squared here to get e raised to power x squared plus a constant. Another example is when we have a quotient. A good example is a function tangent. We know that tan of x can be expressed as sine of x divided by cosine of x. We also see that if we differentiate the cosine function, cosine of x with respect to x, then we are going to get minus sine of x, so that the numerator here, the numerator in this expression can be seen to be a derivative, or a scalar multiple of a derivative of the denominator. It is just the same as the derivative of the denominator times minus 1, because the derivative of cosine of x is negative 1. So in this case, it means that we can apply this method. So we write the integral of tan of x is equals to sine of x divided by x dx. Then we choose u to be cosine of x, the denominator. Differentiate u with respect to x to get minus sine of x. And then make dx the subject. This will give us minus du over sine x. And now we substitute. Our integral was sine x divided by cosine of x dx. It now becomes the integral of sine x divided by u times du over sine x. The negative 1, we can put it somewhere here, minus 1. So sine of x cancels out, and we are left with the integral of 1 over u with respect to u. This is now in the standard form, and so we get minus 1 over u minus logarithm of u, which is negative cosine of x, because u is equals to cosine of x. This one we can write it as logarithm of cosine of x raised to power negative 1 plus a constant, of course, using the rules of logarithms, which becomes logarithm of 1 over cosine of x plus c. But 1 over cosine of x is the secant of x. So that in this case, we get logarithm of secant of x plus c. This is the integral of tan of x with respect to x. This will apply in the same way for the integral of this kind, number 3. We notice that if we look at the function x squared minus 4, and then differentiate this with respect to x, we get 2x. We check the numerator whether the function 2x appears. Although we have 3x, we notice that 3x, we can factor out 3 and then write x, or rather, we can write 3 into x like that, which we can write 3 into 2x divided by 2, which is 3 all over 2 times 2x. In this case, although we have 3x here, we can see that this 3x can be expressed as a scalar multiple of 2x, which is the derivative of the denominator, which is the derivative of the function appearing here under the square root sign. So in this case, we notice that it is possible, therefore, to apply this method, the algebraic substitution, in solving this. So we set u to be x squared minus 4, and du dx is 2x. Then dx becomes du divided by 2x. Then we substitute. The integral becomes 3x divided by the square root of u times du over 2x. Notice that what we have in the square under the square root sign here is what we are replacing with u. Then dx here is replaced by du divided by 2x. So x cancels out. X cancels out here. So we are left with 3 over 2. Then the square root of u. When we write the square root of u, this is the same as u raised to power a half by applying the rules of indices. And now with this one, we can make use of the rules of integration. We increase the power of u by 1. So we have u to power negative a half. This one we add 1 here and divide by minus a half plus 1, which is the new power of u. So this becomes u to power half divided by a half, or even 2 u to power a half. This will be what we get when we integrate. Then we multiply by 3 over 2, which was our coefficient. So when we multiply this by 3 over 2, that is when we write 3 over 2 times 2u raised to power half. Then we get 3 times u raised to power half. But this can be expressed as 3 times the square root of u, because power half simply means we take the square root. And then finally, we substitute back our u was x squared minus 4, and we get our solution. We have another function here. Number 4 is a quotient. In the numerator, we don't have x, but we also note that if you differentiate the function appearing in the denominator. With respect to x, we get a constant, which is 2. And 2 is just a scalar multiple of what we have here, because it can be expressed as 2 times 1. So again, we apply the method. We set u as the function appearing in the denominator. Then du dx is equals to 2 when we differentiate, and dx becomes du over 2. Now, when we are substituting back here, notice that in this integral, we have the limits for x. X is 1 to x is equals to 4. Then we have the function, and we integrate with respect to x. So if we substitute back, we'll have 1 over u du over 2. But the limits for x are x is 1 to x is equals to 4. Now, notice that here, we are integrating with respect to u. We have a function of u, but the limits of integration are in terms of x. So instead of integrating and then substituting back u in terms of x so that we can input the limits, we can also change the limits of integration from x to u. Because we know that u is expressed as 2x plus 3, meaning that at the lower limit here, when x is 1, we can find the corresponding value of u, 2 times 1 plus 3, which will be 5. And at the upper limit where x is 4, we can find the corresponding value of u, that is 2 times 4 plus 3, which is 11. So in this case, we transform the limits so that when we substitute, now we have the limit for u. U starts from 5 to 11. So this becomes a half integral from 4 to 11. This is 5, sorry. This is 5 here. 5 to 11. Then we have 1 over u du. The integral of 1 over u is a logarithm of u. Then u increases from 5 to 11. And this will be the logarithm of 11 minus the logarithm of 5, which we can get the value here. The logarithm of 11 minus logarithm of 5. Then we multiply the result by 1 over 2. So basically, this is how we apply the algebraic substitution. Another kind of integration is the integration by trigonometric substitutions. And one important case is where we have the powers of sines and cosines. So we are going to consider that in this section, where we have the integral of the form, the integral of sine of x raised to power n times cosine of x raised to power m. Then we integrate with respect to x. And in particular, we consider the cases where m and n are positive integers. Now, we consider two cases here. The first case is when m or n is odd, or when both m and n are odd integers, but not the case where m and n are both even integers. So where at least one of m or n is odd, then we are going to apply the identity, the square of cosine of x plus the square of sine of x is equals to 1. And we are going to apply this where we have an odd power. If both powers are odd, then we should just choose 1. So if it is n which is odd, then we see that n minus 1 will be even, and therefore the integral, we can break it down. Remember that using the rules of indices, if you have a raised to power n, then we can always write it as a raised to power 1 times a raised to power n minus 1 from the rules of indices, because the rules of indices simply says that if the base is the same and we are multiplying two quantities, then we add the powers. So when we write a raised to power 1 times a raised to power n minus 1, then we can write as a raised to power 1 plus n minus 1, which is n. So, but now we are going to use this in reverse. So we break a raised to power n into power 1 and power n minus 1. So if it is n which is odd, then we break that into sine of x raised to power 1 and sine of x raised to power n minus 1. So that now this one is, the power here is even. We are assuming here m is even. So then if n minus 1 is even, that is n minus 1 is even, then it is possible to divide this by 2 and get an integer. So it is possible to write this one as n minus 1 divided by 2. This one will be an integer. That one will be an integer because n minus 1 is an even integer. So n minus 1 plus 2 will also be an integer, which can be either even or odd. So in this case, that means that we can write sine of x squared, then the whole of that we raise to the power of n minus 1 over 2. Because when we multiply n minus 1 over 2 times 2, then we get n minus 1, which was our power. So we can break that into n minus 1 over 2, then 2 here. And at this point, we can now use the identity sine squared x is equals to 1 minus cos squared x. From this one, we can make the square of sine of x the subject. Once we replace that, we are now going to replace where here, whatever is inside the brackets there. So we get 1 minus cos squared x raised to power n minus 1 over 2 times cosine of x raised to power m dx. And once we write it in this form, then it will be possible to apply the method of algebraic substitution, the method similar to algebraic substitution, to reduce this into the standard form. Now, to avoid creating confusion, I'll just do an example. An example is easier to follow. So we consider the case where n is 3, m is 2. So integral of sine of x raised to power 3 times cosine of x raised to power 2. We want to integrate with respect to x. So we have sine of x raised to the power of 3, which we can write as sine of x raised to power 1 times sine of x raised to the power of 2. Or even this is sine of x times sine squared x. So we can break our function into that. Now this one, the square, sine squared x, we replace with 1 minus cos squared x. So in our integral we have sine of x times 1 minus cos squared x times cos squared x. We can choose to expand this, but we can also choose to leave it the way it is. So at this point, we are going to use now the method similar to algebraic substitution. We notice that we have the cosine function and the sine. And the sine function that we have here is a derivative of the cosine function, because we know that the derivative with respect to x of cosine of x will give us the sine function. Although there is a negative, but the important thing is that we have the sine function. The other one is a scalar multiplier. So we set u to be cosine of x, then du dx becomes negative sine of x. And dx, when we make dx the subject here, it becomes negative du, all of a sine of x. So our integral here, we are going to replace here cosine of x with u. So cos squared x will be u squared, then u squared here. Then dx is the same as minus du all over sine of 2x. And clearly, you notice that the sign cancels. So we are left with minus 1. We have a negative, this negative. The integral of 1 minus u squared times u squared, which we can expand. This one we can expand and write u squared minus u raised to power 4 du. Then we have a negative 1 here, which we can push inside to have minus u squared plus u raised to power 4, or u raised to power 4 minus u squared when we interchange the terms. This is now in the standard form. So we integrate by increasing the power of u by 1 in both cases. So u raised to power 5 over 5 minus u raised to power 3 over 3 plus a constant. But u is equals to cosine of x. Remember, u is equals to cosine of x. So we substitute back. After integration, we substitute back, not before integration. After integration, we substitute back u is equals to cosine of x. So we get 1 over 5 cosine of x raised to power 5 minus 1 over 3 cos cubed x plus c, which is the solution to that integral. Now, sometimes we may not have both factors, because when we write cosine of x raised to power m times sine of x raised to power n, it is possible to have n being equals to 0. And if n is 0, this one will become 1, so that we have just cosine of x raised to power m. So we have an example here of that kind of a function. We notice that the power is odd, so we are going to break it down. Cosine of x times cosine of x raised to power 4. 4 is even, so we can write it as cos squared x raised to the power of 2, which we then replace now. Remember, we had cos squared x plus sine squared x is equals to 1. Because we have the square of cosine, we are going to make that the subject, which will be 1 minus the square of sine of x. So we replace that, whatever is inside the brackets here, with 1 minus the square of sine of x, and then we can expand this. Or even before we expand, we notice that now we have a cosine and sine, and cosine of x is a derivative of the sine of x. So we take u to be sine of x, du dx becomes cosine of x, so dx rather becomes du over cosine of x. So where we have the sine, we are going to replace with u, so this term becomes u squared. Then dx is equals to du all over cosine of x. And therefore our integral, we have cosine of x, 1 minus u squared, the whole of this raised to power 2, then du over cosine of x. And clearly the cosine cancels out, and then we are left with 1 minus u squared raised to the power of 2 du. The expansion of this, we need to expand this before integration. So you get 1 minus 2u squared plus u raised to power 4 du. And then at that point, now we apply the rules of integration. So the integral of 1 with respect to u becomes u. The integral of minus 2u squared with respect to u becomes 2 over 3u cubed. The integral of u to power 4 becomes u raised to power 5 over 5. Then we add the constant of integration. But u this time was sine of x. So again, we substitute back, and we get our function, our solution in terms of the sine of x. Now, in that case, u and m and n were either both odd, or at least one of them was odd. But now, in the case where both m and n are even, then we choose a different approach. If m and n are both even, then m over 2 is an integer. So we can write sine squared x raised to power n over 2 times cos squared x raised to power m over 2. Then here we are going to choose some different, we are going to choose different identities. So in particular, we are going to write the sine squared x is equals to 1 over 2, 1 minus cosine of 2x, and cos squared x is equals to 1 over 2 into 1 minus 1 plus cosine of 2x. And here, we are going to replace both. So we replace both the square of sine of x and the square of cosine of x with these two identities. We replace both with those two identities. So I want us to do an example. So we have these two identities. These two identities, the square of cosine of x is that, the square of sine of x is that. Then we substitute. But to avoid confusion with this equation 1.3, we just do an example. As before, one of the powers can be 0. One of the powers can be 0 here, so that it is possible to have only one of these factors, like the cos squared x. If we have cos squared x, we replace cos squared x. We replace cos squared x with a half into 1 plus cosine of 2x. So we get a half into 1 minus cos 2x. Then we integrate. We don't need another substitution here. So integrate 1 with respect to x to get x. The integral of cosine of 2x becomes a half sine of 2x. Then we add the arbitrary constant of integration. We can have now cos squared x times sine squared x. So here we are going to replace cos squared x with 1 over 2 into 1 minus 1 plus cos 2x. And we are going to replace sine squared x with a half into 1 minus cosine of 2x. Then we simplify. So we replace cos squared x with a half into 1 plus cos squared x. We replace the sine squared x with a half into 1 minus cos 2x. A half times a half is a quarter. Then we have 1 plus cos 2x times 1 minus cos 2x. When we write 1 plus cos 2x, or basically when we write something like 1 plus a multiplying 1 minus a, we get 1 plus, if we multiply out, we get 1 minus, see the first term is 1. When we multiply 1 times 1 is 1. Then 1 times minus a becomes minus a. Then the next one is a times minus 1, which is plus a. And the last term will be a times minus a, which is minus a squared. Now the middle terms here will add up to 0, and we get 1 minus a squared. Now this, our function is similar to what we have here, 1 plus a, 1 minus a. Only that now a is cosine of 2x. So we get 1 minus a squared, or 1 minus cosine of 2x squared. But now because we still have the square here, we are going now again to replace the square of cosine of 2x is the same as 1 over 2, 1 minus cosine of 2x. Notice that here we have now 2x. So we are going to multiply this angle by 2. So it becomes 4x. 2 times 2x is 4x. So we get 1 minus a half into 1 plus cosine of, this one is plus, sorry, not minus, in our identity. Notice that our identity was this. If we replace this with 2x, then we are also going to replace here, x here, with 2x. So that it becomes 2 times 2x. Because the angle here is double this one. So if this is 2x, then this one becomes 4x. So that is what we have here. Then we can open the brackets in this expression. So we get 1. Notice that here, if we open the brackets, we get 1 minus a half, minus a half cosine of 4x. And this one becomes 1 over 2 minus a half cosine of 4x. So we get a half minus 1 over 2 cosine of 4x. This is now in the standard form. So the integral of a half is 1 over 2x. The integral of cosine of 4x is 1 over 4. The integral of cosine of 4x with respect to x is 1 over 4 sine of 4x. So in this case, because we have negative a half times a quarter will give us minus 1 over 8. So we have minus 1 over 8 sine of 4x, then plus 6. Then we can open the brackets. We have a quarter times a half, which is 1 over 8, then a quarter times minus 1 over 8, which is minus 1 over that 2. So that is the solution to that integral. That's the solution to that integral. So these are basically the methods that we call algebraic substitution and trigonometric substitution. Now, there are many other trigonometric substitutions that we can use to different other types of integrals, but basically where we have the powers of sines and cosine, this is the method that we are going to apply. So for this video, I'm going to stop at that. Then in the next one, I'll talk about integration by parts.